establish some basics about how we represent waves and how waves reflect. So first off, you know from experience that if you drop something in water, you get these ripples that kind of radiate out in all directions. Okay, and you've probably seen this in yourself, and if not, you've certainly seen it on film at some point. But these ripples radiating out in all directions, they're called wave fronts. And then that's part of a way to represent waves. Another way to indicate what's going on with waves is with rays. Which is where the term light rays comes from. That we represent them using rays, and these rays indicate the direction that the wavefront is traveling. They are always perpendicular to wavefronts. We can draw, a number of rays and going out in all directions. And these light rays, and that's where the word light rays comes from. Those rays always move at right angles to wavefronts. Yeah. Now, if you have a small source of electromagnetic radiation, it radiates out in all directions, creating a pattern similar to this, but in 3D, and that would be a spherical wavefront. So we have spherical waves. They're radiating out in all directions. Now, if your source is very far away, like the sun, say, if we take the sun rays hitting the Earth, or if there's a line of sources, like you have a long light that's radiating, you can create what are called planar waves. The wavefronts are a plane, and the rays, essentially, the wavefronts are planes, and the rays are parallel. Now, with the sun, sun is emitting light in all directions. That is a spherical wavefront, but for a given area on the Earth, those rays are so close to being parallel that they might as well be parallel. And so we can consider those to be planar waves. Now, typically, we don't draw wavefronts, and we just use a ray to represent the path of light. It's a very simple model, and it explains many things. It's a good way of diagramming many things that waves do. So we just use rays. Okay, and it's especially useful when we talk about reflection and refraction, which we'll get to later. So there is a property called the law of reflection, and even if you haven't heard of it, you probably know what it is. I think it's easier to draw a picture of the law of reflection than it is to state it in words. So let's say this is a smooth, shiny surface, i.e. a mirror, and it's a flat surface. If we imagine a normal to this surface, if we have a ray that comes in, the law of reflection states that when it hits this mirror, it will reflect back out, and this angle that it comes in at is the same as the angle that it leaves at. This angle is called the angle of incidence. This is the angle of reflection, theta sub I for incidence, angle of reflection. Law of reflection states that the angle of incidence and reflection are equal. They are always the same angle. Now, for a smooth, shiny surface, like a mirror, this is known as specular reflection. I'm not sure what specular means, but that's what it's called. If you have a surface that is not smooth or shiny, on the microscopic level, it might, have some sort of rough kind of shape. And then when light rays come in, it still follows the law of reflection, and they bounce back out at the an angle that is equal, but they're not all hitting a flat surface, and so they bounce off kind of in all sorts of directions depending on how the surface is oriented at the particular point the light ray hits. So this gets light bouncing off in all directions. This is called diffuse reflection. And this is what we mostly see in regular objects. That's how we see their colors. No matter where you are, a blue chair looks blue, whatever angle you're looking at it from. And that's because whatever light source is there, whether it's lights in a room or light from the sun, it's hitting this chair, which is rough on a molecular level, and so the light is bouncing off in all directions, and so it reaches your eye regardless of where you are. And that's why mirrors don't really have a color per se. You look in them and you just see light that's bouncing off of other objects and bouncing off the mirror and reaching your eye that way, because they do reflect back in that regular sort of way. Now, there's an interesting application of reflection, which I just learned about recently. It's kind of cool. It's called a digital micromirror device. And basically, the way it works is that there's just a bunch of tiny mirrors, and tiny, I mean really tiny, like micro, micro. They're on a microscopic scale, a bunch of tiny little mirrors, and they change their orientation as a light source shines on them. And this light source is, it's shooting out light, and it's quickly alternating between red, green, and blue, the three primary colors of light. It's actually cyan, magenta, and green. But and so based on the orientation of these mirrors, that light is projected onto a screen, and it creates an image, and each of those mirrors serves as a pixel, essentially, and it shows a given color based on whether it's bouncing, how much of this red, green, and blue light is bouncing onto a screen. And that kind of eliminates the need for film, in watching a movie or whatever. And I think some theaters use this now instead of the traditional film, but I'm not sure about that 100%. But I thought that was kind of an interesting application. Anyway, a plane mirror is kind of the more physicsy term for a typical mirror that you usually think of, like you see in the bathroom, or I don't know, maybe some of you girls have a little flip-up mirror that you keep in your purse so you can check out what you're looking like. Maybe some of you guys have that too, but you wouldn't admit it. But this plane mirror forms images as light rays reflect from the object to the mirror. They reflect off the object into the mirror and then go to your eye. So take, for example, this candle. Say this is our mirror, and then this is where we're looking at it from. I can't draw a side view of an eye, so just bear with me on that one. But this candle is radiating light out in all directions. But if you're looking at the mirror, you'll only see it in one place. There's light coming off the candle in this direction, and according to our law of reflection, it bounces back with the same angle, and it's going to reach your eye. And these thetas are exactly the same. And then you perceive it as though there was an image. You're looking in this direction, and your brain kind of perceives it as though there's this image that's being formed out over here. Like it's the same as the image would be if there was a candle, and I've drawn this poorly, but if there's a candle an equal distance behind the mirror, if I could make straight lines, yeah, whatever. as though there's this candle an equal distance behind the mirror as it's actually sitting in front of the mirror. Okay, so your brain perceives it as though there is actually a candle back behind. And actually, if I'd drawn this the same height, that would look pretty good. Okay, the same distance behind the mirror as it's sitting in front of the mirror. So this is called, we say this is DO, our object distance, whereas this over here is D sub I, our image distance. And for a plane mirror, the image distance is equal to the object distance. Where the image appears to be, it appears as though there's an object behind the mirror, the same distance away from the mirror as the object is actually in front of the mirror. There are a few key properties of plane mirrors. Property number 1 is that the image you see is upright. It is not flipped upside down, but it is flipped left to right. If you've ever, written anything on a piece of paper and looked at it in a mirror, then you know that it is flipped around backwards. Da Vinci actually took his notes in mirror script. He wrote backwards. I don't know. I guess he thought that would make them harder to read or something. I think it would be pretty quick to figure out, but maybe most people didn't have mirrors in those days. Anyway, and this is actually used. I don't know if on ambulances, at least in the States. I don't know if it's the case here. It'll say ambulance on the front of the vehicle, but it'll be written backwards, and so that people looking at it in their rearview mirror see it, the word ambulance, written left to right as is typical. So that's one way that is used. And I've already said this, but another property, the image distance is the same as the object distance. I can't spell distance, which I've already talked about, like I said. And then third property is that the image is the same size as the object. I didn't explicitly state this, but the image height and the object height are the same, and so are the width and so forth of whatever your object is. Now here's an interesting question. Take a second to think about this and then look at the answer. Question: how big does a mirror need to be for you to see your whole body? So you've got a person here. They want to look in the mirror, and this person has some height. How big does this mirror need to be? Well, let's think about it. In order for you to see your feet, light needs to be able to go from your feet and bounce off the mirror up to your eyes. Okay, and light needs to go from the top of your head, bounce off the mirror, and go back to your eyes. Now, you can, just from a geometric perspective, we know these angles are the same, which means that the distance from your foot to this normal is the same as the distance from this normal up to your eye, because those angles are the same, and your feet and eyes are basically on the same. We're going to be on the same horizontal location, and the same is true. It's harder to draw with a smaller angle, but the angle of incidence and angle of reflection are the same up here too, and so the distance from your eye to the point of contact with the mirror is the same as the vertical distance from that point of contact to the top of your head. So here, you need to be able to, the mirror needs to extend down to halfway from your eyes to your feet. Here, the mirror needs to extend up to halfway between your eyes and the top of your head. So you've got top of head to your eyes to feet, and half of that. So the answer is that the mirror needs to be